Given a black hole with some rotation parameter A, we can ask the question, at what coordinate radius can the innermost stable circular orbit for a massive particle be located, given any particular combination of angular momentum and energy parameter for this particle? Right, so without knowing in advance the angular momentum or the energy parameter of the particle, could we predict where the innermost stable circular orbit occurs for a black hole with a certain mass, capital M, and a certain rotation parameter A? Now, this video will also look at the prograde and retrograde cases for stable circular orbits in the equatorial plane. So we're looking for the innermost stable circular orbit. We'll look for an analytical expression that will give us a location of where these orbits are. Right, so the equation of motion of a massive particle in the equatorial plane is this. All right, for circular motion, we require r dot, that's the derivative of the radial coordinate with respect to proper time to be 0, and the second derivative of the radial coordinate with respect to proper time to be equal to 0. And this second derivative with respect to proper time is also equal to the negative third derivative, the total derivative of the effective potential with respect to the coordinate r. All right, that's all in previous videos. So doing that, we have, here's the first condition, r dot is 0. So say r dot is 0 in here, gives us this equation here that tells us the effective potential is equal to the total energy of the orbit. And here, r double dot, the acceleration, the radial coordinate is minus dv effective dr, the derivative of the effective potential with respect to r. It's his object here, and that is also set to 0. So this equation and this one, they're the two conditions we have. Now that tells us where circular orbits are located. We want to go further now and determine where are the innermost stable circular orbits, because that's important. You think of a black hole accretion disk, what is the smallest radius at which matter can orbit in a stable circular orbit? All right, so we make the substitution, u is 1 on r, so the acceleration equation becomes, that's this one here, that one there, becomes this one in terms of u. Okay, we substituted r, 1 on r for u. Right, now the equation states that dv, the effective potential, the derivative with respect to u is 0. Now, why can we do that? Because wasn't I talking about dv dr earlier? Okay, well, we can do that because dv du is equal to 0 implies that dv dr is equal to 0, because by the chain rule, dv dr is equal to dv du times du dr. So if dv du is 0, then dv dr is also 0. So when we set the condition dv du is 0, we're also saying that dv dr is also 0 as a consequence. Okay, let's make some substitutions to make the algebra look simpler to understand, visually more appealing. So mu is gm on c squared, and capital Q is h minus am c epsilon. That was the result of 2 videos ago. This is all explained in that video and the second last video prior to this one. Made that substitution. So putting that in, dv du becomes this object here. H is the angular momentum of the particle, m is the mass of the particle, capital M is the mass of the black hole, epsilon is the energy parameter of the particle. It could be a small test mass, it could be a laboratory with an observer in it, anything, a massive particle. Okay, so our dv dr becomes dv du, and we have this equation here set to 0. Now for stable circular orbits, we require that the second derivative of the effective potential with respect to r is 0. Okay, so that leads us to the condition that the second derivative of the effective potential with respect to u is 0, because the second derivative of the effective potential with respect to r, second derivative is ddr of dv dr is ddr of dv du times du dr. That's the chain rule there, substituting for dv dr. Now, to operate on that, we're then going to have d du of dv du times du dr times du dr. So ddr is ddu of dv du times du dr, okay? And times then this dv du dr. So this is the product rule or Leibniz rule in operation here. Instead of operating with dr, we're operating with du. And we got that from ddu times du dr is the same as ddr. Then we do this second bit here, dv du, that's the first bit there, times now ddr of du dr. Okay. And what we have now is down here, second derivative dv du times du dr squared, because du dr times du dr, that's squared there, plus here dv du times d2 u dr, because ddr of du dr is d2u, is the second derivative of u with respect to r. Now, given that all of that is 0, that then implies that the second derivative of the effective potential with respect to u is also 0. So requiring dv dr squared is, or the second derivative of v with respect to r is 0, is the same as requiring the second derivative of v with respect to u as being 0 as well. All right. Okay, so dv du is this object here, just repeating that. Then the second derivative of that means that the constant here drops out, this u here drops out, this u squared becomes just u times 2 out the front. So we end up with this equation here. Now this is the condition for stability. Now from a previous video, from second last video prior to this one, we had h squared was this object, epsilon squared was this, q squared was this or this. Okay, so next what we want to do is substitute these three expressions, 1, 2, 3, into the second derivative of the effective potential. That's up here. Substitute it in. And doing that gives us this. Okay, so we have this, and putting them in, ultimately this will come down to an expression that will give us the location of the innermost stable circular orbits. That's the point of doing all this, because this one, dv du squared, the second derivative of v respect to u, is 0 at that location. So, but anyway, so it's all 0. So substituting in h squared, here we go, minus this times epsilon squared, plus this bit here, minus this bit on the end, substituting all of those in. You can see q squared is this bit here, mu here, u here, we've got a 6 there, okay. Epsilon squared is all this. All right, next thing I'll do is establish a common denominator, and we'll make that this u times this term here, because this part of the denominator occurs in all the denominators except here, so we'll put that in. So we'll establish a common denominator of u times this term, okay, everywhere. So we'll have u times that term, where are we here? U times that term, u times that term, times these constants here, so that's effectively 1. Okay, so we now have the common denominator. All that's equal to 0. Well, straight away we know that we can multiply through both sides of the equation by this denominator in order to cancel it out. That'll just leave us the terms in the numerator. So both sides of the equation by the term this, while the right hand side is 0, so that all disappears. On the left hand side, the denominator disappears, and we're just left with the terms in the numerator. And that's these ones. And we settle that to 0. Okay, bit of algebra here, so we'll break that down. So I'll do the bits in the parentheses squared. Let's expand those out. So expanding those out, we have mu times 1 plus 2 times that, plus, okay, that's just expanding out the squared part here. Taking that, if you like, remember, you can think of it as a plus b all squared, okay, is the same as a plus 2ab plus b squared. So a here, okay, b is all of this, okay, so when you expand it out, you're going to have a squared here, 1, then you can have 2 times ab, well, 2 times 1 times b, plus b squared, plus b squared. Okay, expanding all that out. We end up with mu here, plus or minus here, 2 lots of plus or minus this. Just watch out for these plus or minus terms. Keep them in the right order because they cancel terms later on. So just be careful with those. That plus 2 lots of this business here times the mu here. And then here, square all that. So we're going to have for a cubed u squared mu. Sorry, the first bit here is for a squared u squared mu squared, because there's a mu here. Then 2 times that gives us this term here with the 4a cubed u squared mu times that. Plus then squaring the end terms, we have a to the power of 4 u to the power of 4 times the mu from out front. All right, so careful that. Just remember with these double signs, just be careful. Don't lose track of them. Okay, the second set of parentheses squared, this second one here. So we've got this. Again, expanded it out, we've got a minus b. This is all b in here, all that there. So we're going to have a squared minus 2ab plus b squared minus 2 times a is 1 times b is all that plus b squared. So a minus b all squared. When we expand it out, we're going to have a squared u. We're going to have a squared u times 2 times all that, which gives us, I believe it's this one here. Yep, that one. And then the minus here. Now, minus times plus will give us a minus. So we get a minus on top. Minus times a minus will give us a plus. So that sign there, minus plus, it flips direction. It flips order. So be careful about that, because this is an important result. It will cause some cancellation later on. So be careful there. Plus here, then we've got 2u mu all squared. So 4 times the a squared u is 4a squared u cubed mu squared. Sorry. Here we've got plus and minus, doesn't change. All that, 2 times that, that doesn't change. And then here, when we square the last bit there, plus a times all that all squared is the same as minus a times all that all squared. So we just have a plus out front. We don't have a plus minus there. All right, because a negative term squared is a positive result. Positive term squared is a positive result. So we just have a positive result. Next bit, once again, our equation. So putting it all back together now, we have this, and then we have the 2 end terms. Okay, so combining the first 2 terms. Again, just combining these only at the moment. I'm breaking this down a little bit, and then I'll add the other 2 later on. So this and this combined. Don't forget there's a minus here. So in your previous working, all this has to have a minus in front, because on the previous slide, we just looked at plus a squared u times all that. Anyway, so we write them all out here. Write them all out, and then watch carefully, because things are going to cancel. For instance, you've only got a single mu here, so that will carry on down to the final line. But this plus a to the 4 u to the 4 times mu will cancel this minus a to the 4 u to the 4 times mu, so that's easy, so that's straightforward. This one here, 4a squared u cubed mu squared minus 4a squared u cubed mu squared, they cancel, they're gone. All right, what have we got here? We've got a here I've got a 4a cubed u squared mu plus or minus. And then down here I've got 4u squared mu a cubed that, but just watch here. Plus, when the plus term is operating here, we have plus all this, but the corresponding term down the bottom here is the minus. All right, so we have minus the same amount, the same quantity. Up here, when the lower sign is operating, we have minus all this, but by the same token, over here, the lower sign is positive. So those 2 are going to cancel out, they're going to disappear. And that's why those order of those signs must be kept very carefully. Okay, so that's all gone. What we have here is, then we have a 4a squared u squared mu. That was combined with this one here, 2a squared u squared mu, which gave us the 6 lots here. Okay, we have this bit remained untouched, and this term here remained untouched. It came down here. Okay, so that's what we have from combining the first 2 terms. Adding the last 2 terms to this result, so this plus this third last term and 4th term. Okay, so we have all that. Adding on all that is equal to 0. Keep going, next page. This leads to just writing out again. Here we are now writing out those last 2 terms without the parentheses, expanding them out. Now again, watch out. Again, we only have a mu by itself up here, so that remains there. This first term didn't cancel with anything, so that carried down. Now here, what we did have is this plus 6a squared u squared mu minus 6a squared u squared mu, well, they go. This minus a squared u and plus a squared u, that all goes. I seem to have lost a plus sign there, should have been at the beginning. And this minus 6u mu squared, that'll stay. This term here will stay. There's nothing else to match it. And so what happens here is we're left with just minus 3a squared u squared mu. That sits here like this, plus that, the first and second terms stay here. Okay, now the next thing we're going to do is we're going to change this. Okay, we can actually express it in a different form. In fact, we can express it in a form where there's a square root of u cubed times mu. Okay, so one thing we can do now, we've got mu in every single term, and the equation's equal to 0. So we can just divide through by mu. That'll give us a plus 1 at the front. Then we'll have plus or minus that term there. Then we'll have 3a squared u squared minus 3a squared u squared. And then here, the mu is gone. We've still got this. Minus this is equal to 0. Next thing now is I'm just going to rewrite that term. That u there could be put back inside the radical sign there, back in under the radical sign in its form of u squared. So if I take u squared times u, I get u cubed. But if I had u squared times u here, then the u squared could be square rooted. I get u. So I could put it back inside to give it u squared times u that's there gives me a u cubed. So I get u cubed mu, which matches this u cubed mu. Okay, now just watch out because here, this term here, plus minus 4a square root u cubed mu, here it is. Okay, this has the opposite arrangement of signs because this one is this 12a square root of u cubed mu is minus plus, whereas this is plus minus. Okay, so let's say the top sign is operating. We have minus 12a times that. The top sign here is plus, so we have plus 4a times that. Well, minus 12a plus 4a is minus 8a. All right? And then plus 12a minus 4a is plus 8a. Okay, so these two are combined down to this to give you minus plus this, minus the 6 mu on the end. Okay, and I'll just rewrite that in a slightly different order. 1 minus 3a squared u squared minus 6u mu minus plus that object there is 0. This equation will give us the location of the innermost stable circular orbit for any black hole of mass m, which is contained in the mu there, because remember mu is gm on c squared, and a is the spin parameter of the black hole. Okay, u is equal to 1 on r, and that'll tell us where the innermost stable circular orbits are. All right, so next we substitute, to set that more clearly, next we substitute u equals 1 on r. Put that in there like that. Okay, here we go. Y now, oh yeah, okay, so I'll pull this out front here. Okay, now multiply through by r squared. We get r squared minus 3a squared minus 6r mu minus plus 8 r squared of r mu is equal to 0. Now, we need to sort out the signs here. The minus, there's one equation which has minuses in it. That's the top sign operating. That's the retrograde or counter-rotating orbit case. The prograde or co-rotating orbit case is this one with a plus sign underneath. All right. Now, retrograde means that the particle, the mass, the observer, whatever it is that's orbiting the black hole is orbiting in the opposite direction to the rotation of the black hole itself, so retrograde. And when the mass or particle or observer or laboratory or whatever it is that's orbiting the black hole is co-rotating with the black hole or rotating or orbiting in the same direction as rotation of the black hole, then we have the prograde case. Okay, so the plus sign is prograde, the minus is retrograde. Okay, solving these equations gives us the value of the coordinate radius at which the innermost stable circular orbit can be found, there being no others possible below these values. This is the innermost stable circular orbit possible. That's what this equation gives you. You don't have to worry about, in the previous video, for a given value of h and for a given value of epsilon, where is the innermost stable circular orbit? Well, we did that there. Here, this equation will give you where that is. All right, so using the following constants set to 1, just to simplify the algebra and make things look visually clearer. It's easier to work in these geometrized units. G equals m equals c is 1. Set the following constant set to 1, the spin parameter becomes all that equal to 1, and a is gm on c squared, but since g, m, and c are all 1, the spin parameter simply becomes the dimensionless spin parameter a star. So for a given spin parameter value a, we can numerically solve for the related innermost stable circular orbit value r. So for example, if a is 0.2 plus 0.2, then you've got r is 5.3294. Okay, gm on c squared, if you put the units back, but within geometrized units, everything is set to 1, you have just 5.3. All right, for prograde orbits, we can look at different values of a, 0, 0. I'll put 20 of them in here, basically 0 0.1, 0 0.15, 0 0.2, 0 0.25, and so on. You get the idea right up to 1. Okay, for retrograde orbits, the same thing. We can plot those values. I've done all that numerically, and you get those values, the R value, by numerically solving the previous 2 equations on the previous slide. Okay. Remember, for the minus term was the retrograde orbits, and the plus term was the prograde orbits, if you remember on the previous slide. So using a software package, you numerically solve for these. Okay, so that's prograde, retrograde. Okay, now we can plot these values to show the following. Okay, so here is a plot. A on mu, remember mu is 1 here, so it doesn't matter, but if it wasn't, this mu would be, so that'd be a times c squared on gm. Same here, r times c squared on gm, but mu is 1. Okay, then you would plot that. So for the retrograde orbit here, as the spin of the black hole increases, the coordinate radius at which the innermost stable circular orbit can be found increases. Perhaps not intuitive, that result. And in the prograde case, your mass, your particle, your observer in a laboratory rotating around the black hole. In the prograde case, so here's the observer or particle rotating with the black hole. As the spin parameter of the black hole increases, as the spin rate increases, rotation increases, the radius at which the innermost stable circular orbit occurs decreases. It decreases right down to 1. So in the extreme Kerr case, A equals mu is 1, the innermost prograde orbit stable orbit lies at R equals mu. Okay, very, very, very interesting. So the faster the black hole gets, if the particle's co-rotating with it, then the innermost radii, the radii at which the innermost stable circular orbit can occur, in the extreme Kerr case, is at R equals mu. You know, like R equals 1. See over here on the left here, R is 1. Where my cursor's pointing there, R is 1, and A is 1. Wow. And at the end, there's very quickly. Okay, so in the general case there, the faster the black hole rotates, then the co-rotating particle with it can move in closer for a stable circular and reside at a stable circular orbit closer and closer in. Whereas in the retrograde case, it goes completely the opposite way. The innermost stable circular orbit occurs further and further out for the faster the spin of the black hole. Anyway. All right, so let's consider the energy parameter for each of these innermost stable orbits. So that is for each value of the spin parameter A, so the black hole's got some spin parameter A, rotating at some rate A, and its associated value of R is what we're trying to find for some given value of A. What is the energy parameter epsilon of the particle for that orbit? So here's our particle. Our mass, our observer in a laboratory, rotating around, orbiting around a black hole, okay, of mass m at some distance r, okay, some value of a. What is epsilon? All right, what is epsilon? That's what we're going to have a look at. because if you remember, epsilon was the energy of the orbit divided by the energy of the particle in its rest frame far from the rotating source. So in a frame far from the rotating source at rest, what is the rest frame energy of the particle, which is mc squared, and epsilon is the E of the orbit, the energy of the orbit divided by mc squared, and epsilon is that ratio. Epsilon here expressed in terms of mu, u, and a is this, as found in previous videos. Okay, replacing that with r, we get this, putting that in there. Okay, so what's the energy parameter for these innermost stable orbits? Now here, R will represent innermost stable circular orbits that we've been talking about in the previous slides. But what parameter of epsilon do we need for that? What parameter of epsilon is there? All right, so we can use this expression to generate the ordered pairs to the form A epsilon. So we choose A. Again, we'll use 0, 0.05, 0.1, 0.15, 0.2, 0.25, and so on up to 1. Okay. And that's prograde orbits. If we just plug in a software package and just substitute in, we get the values out. And retrograde orbits, we get these. And what's interesting now is to plot these. Okay, so here's epsilon on the vertical axis. Here's A. Again, if we were using non-geometric units, we'd have A times C squared on GM. Okay, now, if I forget to label my diagram, I most certainly have. Okay, the retrograde orbit is the top dotted lines here. I forgot to label my diagram. Whoops, and this is the prograde orbit here. Okay, so the energy of a particle at rest at infinity is mc squared. That's in its rest frame. While the energy of the same particle in some orbit around the black hole is E equals epsilon times mc squared. The difference between those two quantities, okay, is the gravitational binding energy of the orbit. So E binding is epsilon minus 1 mc squared. It's negative value binding. So the difference between these two quantities is the gravitational binding energy of the orbit. Okay, the gravitational binding energy, E binding, is greatest for prograde orbits, and so they are more tightly bound orbits because the E binding has a larger value. You can see the difference between the value and epsilon is 1. Epsilon 1 is that straight line at the top here. The difference between that top line and this one, for instance, is huge compared to, say, for the prograde orbit compared to the retrograde orbit. Okay, this straight line thing represents the retrograde orbit, and this one here represents a prograde orbit. So this particle is rotating with the black hole, and it's more tightly bound because the binding energy, which is the difference between epsilon equals 1 and this value of epsilon down here. Okay, and the difference, so prograde orbits have higher binding energy, and so they are more stably bound. Okay, so E binding is greatest for prograde orbits, and so they are the more tightly bound orbits. The extreme Kerr case, A equals mu as 1, is the most tightly bound of all. As you can see on the previous slide there, it's just about down here somewhere. The difference between this point here, which is 0.67 or something like that, to 1, I mean, it's huge. Okay. All right, next bit. Now, a particle, so how is that useful? Because a particle co-rotating with a black hole is more tightly bound than one rotating in the opposite direction. So a particle in an accretion disk around a black hole experiences turbulent viscosity. That's kind of friction between different rings. So matter in different rings orbiting the black hole, between the different rings, they're moving at different speeds, and so there's a friction there, okay, a viscosity there, and it's a bit turbulent too, but there's a viscosity there, and so rings lose, the inner rings lose angular momentum, and it's through this process, this frictional process, they can lose energy and spiral inwards onto the compact mass, onto the black hole itself. So a particle in an accretion disk around a black hole experiences turbulent viscosity that causes it to lose angular momentum, and so it moves in towards the central mass. Now, as it moves from infinity to the innermost stable circular orbit, it releases energy mostly as radiation. Okay, it's losing angular momentum, so it's giving up energy. Now, the efficiency, epsilon accretion, of the accretion disk is the fraction of rest frame energy released in moving from infinity to the innermost stable circular orbit. Okay, so it's back to that binding energy again. You can think of the binding energy as in some orbit is the energy you'd have to put in to break the particle out of that orbit and take it out to infinity. Okay, now so here the efficiency, the accretion of the accretion disk is a fraction of rest frame energy released in moving from infinity to the innermost stable circular orbit, and that's equal to 1 minus epsilon. Remember, epsilon is that proportion between 0 and 1. So for a Kerr black hole with A is 0.999, using the formulas earlier, substituting in, E accretion is 1 minus, now epsilon for that is 0.666 approximately, and that gives us about 33.4%. So a particle has lost 33, like a third of its energy in falling from infinity to the innermost stable circular orbit, about 33.4%. That's a huge amount of energy, which is liberated largely as radiation. I mean, that's phenomenal, and I'll just show you why. So the same situation with accretion disk around a Schwarzschild black hole results in epsilon accretion being approximately 5.7% of its energy. Of the energy of the particle's loss is given out as radiation. It's converted away as radiation, so it's lost. So 5.7% is a fair bit less than 33.4%. But just to compare both of those figures with something that's maybe a little bit more familiar, is a nuclear fusion of hydrogen into helium has an efficiency epsilon nuclear fusion of approximately 0.7%. And 0.7% of the mass is liberated as energy, as radiation. So these black hole accretion disks then are liberating huge quantities of energy. I mean, absolutely phenomenal. Okay, so I'll leave it there. Finish now.